Linear Control Systems, lecture number 5. I'm your instructor Yasir Amir Khan. This lecture is about stability, and in this lecture we will discuss Routh-Hurwitz stability criterion and how to make Routh array and how we can use Routh-Hurwitz method to determine the stability of the given system. Routh-Hurwitz criterion. In this topic, basically the problem is that we are concerned about the stability of the given system. We have a transfer function that is basically representation of a system, and we want to see that whether that system is stable or unstable. Now, if we take the denominator polynomial and find its roots, then those roots are called the poles of the system. We look at those poles, and on the basis of that pole we can tell that whether the system is stable or unstable. Now, how we can tell that? If the poles have their real part, that is positive, then this means that the pole is located on the right hand side of the geometric axis. If the pole is a complex number, it has an imaginary part and a real part. For example, if we have a pole 2 plus 5j, it has a real part 2 and an imaginary part 5j. We look at the real part. In this case, we look at 2 and see whether if it is positive number or a negative number. If it is a positive number, this means that the pole is located on the right hand side of the geometric axis in the unstable region. So if this is the pole, 2 plus 5j is the pole of a system, then that pole is an unstable pole that is located on the right hand side of the geometric axis. This means that the given system is unstable. If a single pole, even as one single pole goes on the right hand side of the geometric axis, happens to be on the right hand side of the geometric axis, then the given system is unstable. So what we basically do is that we find out the poles of the system, then we look at the real part of the poles, and on the basis of being positive, negative, we deduce that whether it is a stable system or unstable system, or marginally stable system if it is on the geometric axis. Now what we have to do is we have to actually evaluate the roots of the denominator polynomial. We have to find the poles of the closed loop system, given closed loop system, or the given transfer function. Routh-Hurwitz method gives us an alternate way without actually solving and finding out the poles, finding the roots of the denominator polynomial, that are the poles of the system, without actually evaluating them and looking at their real part and so on and so forth. Without doing that, we can, using Routh-Hurwitz method, find out whether the given system is stable or unstable, and if it is unstable, then how many unstable poles are there. So this is basically the main strength of the Routh-Hurwitz method. So this is what we will be discussing in today's lecture. Now let us see a bit of background of before we start the actual topic of Routh-Hurwitz. Consider that we have a transfer function. We have a closed loop transfer function. Closed loop transfer function will be explained in the slide number 6. What we mean by closed loop transfer function. For the time being, consider that we have this transfer function, t function of s. It's the transfer function of a given system. We are basically concerned about finding whether this given system is stable or not, and the transfer function of that given system is t function of s, and the transfer function is s minus 1 upon s plus 2 and s minus 10. In the numerator we have a 0, and if we equate s minus 1 to 0, we get s is equal to 1. That is called the 0 of the system. And in the denominator we have two poles. If we equate s plus 2 equal to 0, we have s equals to minus 2, and if we equate s minus 10 equal to 0, we have s is equal to 10. So we have two poles. One pole is minus 2 and the other is at 10. This pole, which is shown in red color, is actually the pole that is on the right hand side of the geometric axis. This pole is in the unstable region. This means that this pole, because of this pole, our given transfer function is, and the given system is unstable. So we have a system which has a pole. That pole is on the right hand side of the geometric axis. Therefore our given system is unstable. Now what's so bad about this unstable system? If we find its step response, we give a step input to the system. Input is signal r function of s is 1 upon s. Unit step is 1 upon s. We multiply that with the transfer function t of s. Then we get the response of the system c function of s. That response of the system is shown over here in this slide, s minus 1 upon s, s plus 2 and s minus 10. We can split this into three partial fractions. In order to solve it and convert it into time domain, we can split this into partial fraction expansion. We can make partial fraction expansion. Now you can find the coefficients of partial fraction expansion. You must have seen that in the previous lectures. I had given exercise as well. And if we take the inverse Laplace transform and we using the table of Laplace transform, we can find that c function of t equals to a plus b e raised to the power minus 2t plus c e raised to the power 10t. This term c e raised to the power 10t, this is actually the shown in red color is the culprit. This grows and becomes unbounded with the passage of time. As the time proceeds, as the time increases, this term keeps on increasing and increasing and becomes unbounded. So what is happening is that we have given a bounded input but we get an unbounded output. So this makes this gives us this thing tells us that the given system is unstable. It violates the Bibo stability of definition, bounded input, bounded output stability definition. We are giving a bounded input, output should remain bounded, but that is not the case over here. Therefore the given system is not stable. So this is what is happening when we have pole on the right hand side of j omega axis. The given system is not stable, it's unstable. Now how we find out the stability? So what we do is that we look at the roots of the denominator polynomial. These roots of the denominator polynomial are actually the poles of the system. We look at those poles and we look at the real part of those poles. What is written over here is that the real part of the pole should be less than 0 for stability. If that is so, if this condition is fulfilled, then the given system is stable. Otherwise the given system is unstable. It can be marginally stable as well, but for stability, if you want to declare the given system stable, you have to look at all the poles, and all the poles should have their real part strictly negative, less than 0. Then real part, then the given system would be called a stable system. Now in order to understand Routh-Hurwitz method, let's consider this given system as shown in this block diagram. The transfer function of the plant is 1 upon s plus 1, and in the feedback path we have a sensor with a gain of 1, and there's a negative feedback. So this is a closed loop system, and first of all we need to find its closed loop transfer function. We are basically interested in finding the stability of this closed loop system. We are not concerned, we are not focusing on the stability of the plant at the moment. We can do that as well separately, but right now our concern is the overall system. That is, the system has an input r function of s and has an output c function of s. The closed loop transfer function t function of s would be equal to c upon r. We want to find whether this c upon r, this transfer function, this closed loop system as shown in this block diagram is stable or unstable, and how we can use Routh-Hurwitz method without actually evaluating the closed loop poles of the system. How we are able to tell whether the system is stable or unstable, and if it is unstable, then how many poles are on the right hand side of the j omega axis. Closed loop transfer function. Now here in this slide you can see that using the formula for the closed loop transfer function g upon 1 plus gh, we get the closed loop transfer function for the system given in the block diagram in the previous slide. So the closed loop transfer function t function of s is equal to c function of s upon r function of s, and that is equal to 1 upon s plus 1 divided by 1 plus 1 upon s plus 1 into 1. It is on the basis of this formula given here, g upon 1 plus gh. On the basis of this formula g upon 1 plus gh, we get the closed loop transfer function. In this transfer function, in the denominator you see 1 plus 1 upon s plus 1 into 1, that is 1 plus gh, and we call it characteristic polynomial. This denominator of the transfer function is called the denominator of the closed loop transfer function is called the characteristic polynomial. Now let's do a bit of algebraic manipulation. Again, the denominator 1 plus 1 upon s plus 1 into 1 is the characteristic polynomial 1 plus gh. So if we do a bit of manipulation, we get finally 1 plus 1 upon s plus 2, as you can see here. Again, s plus 2 is the characteristic polynomial. This is called the characteristic polynomial. S plus 2 is the characteristic polynomial. It is the denominator of the closed loop transfer function. When we equate s plus 2 equals to 0, then this becomes an equation. This equation is called characteristic equation. When we equate the characteristic polynomial to 0, then that equation is called the characteristic equation. Now we have a characteristic equation. We can find the roots of the characteristic equation, and those roots are also called the eigenvalues. They are the poles of the closed loop transfer function. If it's a degree 2 polynomial, then there will be 2 roots. If it's a degree 3, then we have 3 roots. These are the also called the eigenvalues, and they are the poles of the closed loop transfer function. The poles of the closed loop transfer function are the roots of the characteristic equation, and they are also called the eigenvalues. Now there is a condition. The condition is that if the real part of all the eigenvalues, that is real part of all the poles of the closed loop system, that is real part of all the roots, is strictly negative, that is it is less than 0, then we say that the given system is stable. Otherwise it's not stable. Stability condition is that the real part of all the poles should be negative. Now here we have the polynomial s plus 2, and characteristic equation is s plus 2 equals to 0. If we solve it, that is we get the root s equals to minus 2. This can be written as lambda 1, the only eigenvalue, and that is this root is the pole of the system. Now its real part, it's a real number, so the imaginary part is already 0, so the real part is minus 2, so the real part is less than 0, therefore our given system is stable. So it's very obvious and it's clear from this case, but we are just checking the condition, explaining the condition over here. For a system which has more than one root, you have to apply this condition on all the roots. They all should have followed this condition, then your given system will be stable. This all what we have seen so far can be checked by Routh-Hurwitz method as well. In order to apply Routh-Hurwitz method, we need to construct Routh array. Let us learn how we can construct Routh array. In order to understand this method, let us consider a characteristic equation give 1 plus gh given as s cube plus 4s square plus 2s plus 4 equals to 0. With this characteristic equation, this is actually the denominator of the closed loop transfer function. The transfer function is not given here, just the denominator is given here, and that denominator is called the characteristic polynomial, and when we equate it to 0 we get characteristic equation. So we have a characteristic equation of some system which is written over here in this slide. We basically want to find out whether the given system would be stable or not based on this characteristic equation. We will not find the roots of this equation. We will not find the poles of the closed loop transfer function. Without doing that, by the Routh-Hurwitz method, we will determine whether the given system is stable or unstable, and if it is unstable, how many poles are on the right hand side of j omega axis. So without actually finding and calculating the poles by using the method of Routh-Hurwitz, we can find out whether the given system is stable or not. We construct the Routh array in this way. First of all, write the S in descending powers as shown over here, and draw the lines. You should have your notebook with you and try to do all these steps along with these slides. Now in the next step, write the coefficients of S. The coefficient of S cube is 1, so write 1 in front of S cube. Then the coefficient of S square is 4, write 4 in front of S square. Now remember that when we use the coefficients to fill the Routh array, what we are doing at the moment, we have to write the coefficients only in the first two rows. So far in the previous slide you have seen that we have written the coefficient of S cube as 1 in front of S cube, then we wrote the coefficient of S square in front of S square. Then you will not go downwards, but rather you will write the coefficient of S2 in front of S cube after 1 as shown over here in this slide, and the coefficient of S raised to the power 0, that is 4, that comes in the last in the polynomial. You can pause the video and go back and see that characteristic polynomial again. The 4 that comes with S raised to the power 0, that is 4 that comes alone without any S, that 4 is written in front of S square, and remaining you fill the rows, both of the rows, first and second row, the row of S cube and the S square, with zeros after these numbers. So when the coefficients of the polynomial end, you fill the remaining columns in row number 1 and 2 with zeros. You don't later on you will see that we don't actually write these zeros. It's understood they are filled with zeros, but at the moment you should write zeros. So let me repeat again. The coefficient of S cube was 1. I wrote 1 in front of S cube. Then the coefficient of S square was 4. I wrote 4 in front of S square. Then the coefficient of S was 2, so I wrote 2 in the first row, the row of S cube. This is what you should note. And then the last number was 4, that was written below this 2 in the row of S square. And then after that we fill it with zeros. This is how we make the array. Now the entries after these two, what we have filled with the coefficients, in the next row is b1, b2, b3 and so on. b3 is not over here because it's understood it's 0. We will see that shortly. Then in the next row we write c1, c2, and remember that the array forms in the upper triangular form. Now let us see how we can find the value of this entry b1. b1 is found by this, as shown over here, -1 upon 4, determinant of 1, 4, 2, 4. As you can see, we always write as -1 upon the entry just above b1, that is in our case 4, as shown by these lines. So 4 comes from here, from the front of S square, that we write over here, -1 upon 4. Then we have the determinant. In the first column of the determinant, we write the two entries above b1, that is 1 and 4. These two entries form the first column of the determinant. Then in the second column of the determinant, we write the entries next to b1, 2 and 4. They are written over here. Then we evaluate this determinant and solve this to get the value of b1. Now solve it, open the determinant, solve it, and you can see that we get 1 answer. 4 minus 8 is -4, that becomes +4 divided by 4, so it becomes 1. So we have b1 equals to 1. Now let us see how we can find out b2. b2 is the next entry and adjacent to b1. For b2, for finding b2, again we write -1 upon 4. this 4 is the same that was above b1. This thing is not changed. For b2, if we had b3, again we would have done same minus 1 upon 4. So we always write minus 1 upon the entry above b1. For b2 we use the same 4 as shown by the arrow over here. Is it clear? And then we go into the determinant. In the determinant, the first column is again the same. They are those same entries 1, 4 that are above b1. We are finding b2, but in the first column we are writing 1 and 4, the entries that are above b1. This is the way it is done. We are not going into the details of the derivation, how we get that, but try to understand and follow this method, that we do it this way. Now the second column of the determinant. Now here comes the difference. Here we write the next column, the column next to b2, the column in the rows above b2 next to b2 as shown by this arrow. So 0 0 comes from there. Now solve this to find b2. You can see that since the complete column is 0, therefore the determinant would be equal to 0. So b2 turns out to be 0. So here we have the Routh array that is being completed. We have b1 equals to 1, b2 equals to 0, then b3 will again be equal to 0. Why? Because if you look over here, we have a complete column of zeros. We have 0 0 in the rows above b3. The complete column has 0 0. So when you will make the determinant, in that determinant there will be a complete column of 0. So b3 will be equal to 0. We are not actually solving it, but you can try it in rough. You will get b3's value equal to 0. Why is that so? Because whenever we make the determinant, we put in the determinant, the second column is always taken from the column next to the entry we are trying to find. Like in previous case, you have seen that when we were finding b2, for b2 in the determinant, the second column was taken from the column next to b2, from the rows above b2. Similarly, when we would be finding b3, we will take the second column from the column next to b3 as shown over here. And by default, as we have already seen, that we always fill the remaining entries by 0. So they are by default filled with zeros up to the infinite. So if you will evaluate b4, that will again be equal to 0, because next column will have only zeros, and so on and so forth. Now we have c1, c2. We find c1 in the same way. For finding c1, in order to find c1, we have minus 1 upon b1, because above c1 we have b1, and b1's value we had already seen, it is 1. And then we have the determinant. In the determinant, in the first column, we write the entries above c1. In this case, the entries above c1 are 4 and b1, so we write those in the first column. And in the second column, we have the entries from the rows above c1, but from the next column, that is 4 and b2. So we have written 4 and b2 over here. By solving this, by substituting the value of b1, b2 as shown over here, and solving it, we get the value c1 equals to 4. So you can see that c1 equals to minus 1 upon 1, because b1 is 1. Then inside the determinant, the first column has 4 and 1. The second column has 4 and 0, because b2 is 0. When we evaluate the determinant, we get c1 equals to 4. Now we find c2. c2 will always be 0, because we have an upper triangular form, but we can you can verify that as well. When you find c2 is equal to minus 1 upon b1. Again we write b1 over here, because for finding c2 we will write the entry above c1, just we have seen earlier. So minus 1 upon b1 determinant of 4 1 then 0 0. Since in the second column, as written over here, in the second column we have both rows equal to 0, therefore when you will evaluate the determinant, C2 will be 0. So what you should do is try to evaluate it. And the second thing is that no matter whatever the case is, we always have Routh array in upper triangular form. We will only have one entry in front of s raised to the power 0. Rest all the entries in that row will be 0. So if you find C2, that will be 0. If you find C3, that will be equal to 0. And the reason is that the determinant will have a complete column filled with zeros. Now here the Routh array is complete. You can see that we write the array in this way. We don't write the extra zeros over here. It's in upper triangular form. We write 0 over here when b2 was equal to 0, so we have written a 0 over here. If you want to write the fill the remaining rows with zeros, so that's fine initially, but later on you will get used to it. This is the form in which the array is normally. We in the row of s cube we have 1 2, then we have in the row of s square we have 4 and 4. In the row of s1 we have 1 and 0, that the b1 and b1 is equals to 1 and b2 equals to 0. Then in the row of s raised to the power 0 we have 4, c1 equals to 4, then c2 was 0, and then this way we have this in the upper triangular form. So this is this array, Routh array is now complete. Now what to do next? Look for the sign change. In the first column, look in the first column, is there any sign change? There is no sign change in the first column. And now here you can see that there is no sign change in the first column. We have 1, then 4, then 1 and 4. As we move from top to bottom, 1 4 1 4, there is no sign, all are positive numbers, so there is no sign change. What does this mean? This means that there is no pole on the right hand side of j omega axis. There is no unstable pole. The given system is stable. Since there is no sign change, therefore the given system, of which this was the characteristic equation, that system is a stable system. We don't have any sign change. If all the entries were negative numbers, for example, then again we would not have any sign change. We have all positive entries over here, so there is no sign change. So this means that the given system is stable. There is no pole on the right hand side of the j omega axis. This means that the system with the characteristic equation given over here, which we have used for constructing the Routh array, that system is a stable system. Now we have another example. This is totally new. Some characteristic equation that is not given over here, we suppose make it Routh array, and we get this thing over here. You can see that we have in the first column, when we move from top to bottom, we have 4 -2 3 1. Now what about this kind? What about this kind of system which has a Routh array in this form? Now in this example, as you move from 4 to -2, then -2 to 3 and 1, how many sign changes are there? Think about it. There are 2 sign changes. As you move from 4, as in the first column, as you move downwards from 4 to -2, there is one sign change. Then from -2 to +3, there is another sign change. 4 is a positive number, -2 is a negative number. As you move from 4 to -2, there is one sign change. And as you move from -2 to 3, there is another sign change, -2 positive. Then as you move from 3 to 1, there is no sign change. 3 is positive, 1 is also positive. So as you move from 4 -2, then 3 1, there are 2 sign changes. These 2 sign changes mean that there are 2 unstable poles. In this example, for an characteristic equation that is not shown over here in this example, that characteristic equation has 2 roots which are the poles of the transfer function. They are in the unstable region. They are on the right hand side of the j omega axis. So when we have 2 sign changes, this means that 2 poles of the system are on the right hand side of j omega axis. So the given system is unstable. So this method not only tells you whether the given system is unstable or not, it also gives us the information about the number of unstable poles, number of the poles that are on the wrong side of the j omega axis. Now here is an exercise for you. We have a closed loop transfer function, t function of s, given over here. and its characteristic polynomial, which is the denominator of the transfer function. Closed loop transfer function's denominator is called the characteristic polynomial. It is shown over here. You have to find whether the given system is whose transfer function is t function of s, whether it is a stable system or an unstable system. And if it is an unstable system, you also have to find out the number of poles that are on the right hand side of j omega axis. If you have any kind of confusion, do not hesitate to contact me through WhatsApp or email. Thank you.